Assalamu alaikum. Today and welcome to my channel. Today we would be doing different logic gates with Boolean function, Boolean expression, and De Morgan's law using Quartes software. As you all know, software is the main building bone of engineering, and in this you can build multiple functions and could see that how it would be produced. And it a Quartus basically provides a vast and multi range of to an engineer to not only design and set to its equation and design, but also implement and show it how that it is performed. So we will simply go to Quartes. I've installed Quartes 2, Quartes 15 over here. Now I've already produced formed the circuit and which I would be like to form. So I'll simply go to open circuits. If you wanted to create a new project, you can go to the new project, but as I have already created it, I'll simply go to new open projects. So first I will be starting from AND gate because it would be the major and building one of here. I'll simply be connecting it and okay. So it would be taking some time to open it. So here my AND gate is open, so I'll simply go to this, and this is my AND operation. So what is an AND gate and how it is proved? So simply, as you can see, this in Proteus there is a method of in Proteus there was a method to just connect the circuits and you are done. But in Quartes there is a method to write Verilog HTML codes. I have used Verilog HTML codes to define to write my circuit and use their implementations. So in this Verilog HTML code, the start should always be with the module. This is the you do the circuit in the C++. We start in C++. We start with include IOStream. In Verilog, we start with module and we end it with end module. This is the starting and ending of the phrase. With the module, the name of the file, and the input, the variables used. So first we will go from module and test, that is the name of my file. Then the inputs are A, B, and Y. You can also write it C or anything else as you like. Then this is my input declaration. We have input is A and B in my case, and the output declaration is output is Y. Now the ports that data type is that wire is equals to Y. You can also use wire as Y, and you can also use wire as X and use the sign as this. So in my case the wire is Y, and then we assign as Y is equals to A and B. This is the symbol of AND gate over here. This is an AND small and written and B. So this will be the circuit AND module. We will simply press to run the circuit. It will take few moments and then it will be running out. If any of the error is produced, you should be circling it and cancelling it out. So how can we remove the errors? The mostly errors are that if the name of the file that you have written is not the same as the name of the file written with AND gate, it will not produce the circuit. And similarly, there are some other errors that are produced, but you can see the errors over here in flow of messages. It shows everything that happens over here. Like over here, you can see that what is going on and what are the messages displayed. So it will take few moments and then it will be compiled and completely. Although this takes some time, but this is a function of Verilog, but it will produce eventually. Although my circuit was already run, so in the next few videos that all of that I would be doing, I would be showing you that already run circuit so that we could save time and I could explain you much better. Uh, in this, if I wait for every circuit to be run and then produce it, so it would take a lot of time. So I would be just showing the one implementation and then the rest I would be explaining it, and we would be doing it the rest of it. Now, Verilog and HDL, until and it is combining, we could discuss Verilog and HDL code and languages. The Verilog and HDL code and languages are really easy to implement the circuit and to define that how it is proved and implemented. This Quartes has a speciality to adjust according to your design and created design and your created simulation. So it will also in ahead when I would be explaining it, I would be also be showing you that it has one of the best quality of reducing the circuits in HDR and interface as well. You can also find the waveform, how it is produced, the logic gates waveform, and also their interface, that how they look like the circuit looks like with just using the equations. You would be able to formulate the results and also circuit. So this is the major comeback of Verilog circuit. So here my all of the simulation is proved and is run, and it does not have any errors. So I'll simply close it. I'll go to AND gate, press right button, and then click locate node. Then I locate node. I'll be going to locate in L viewer. So in this it will take few seconds and this will show you how the circuit would be looking at. So this is my equation and this is perfectly an AND gate reduced and this is highly proven. So by this it is already proved. But then we can also see the simulation in the waveform by simply going on new. You can either go from here or you can select file and you can go to university program VWF. This is you gonna select it and press OK button. Then here you can see a file is open. Use this white bar empty part. Use right click it and here it is written insert node or bus. Just select it. It is then go to node finder. You can see the list is empty. You go to list, click it. If you want to click everyone ahead like separately, singly, you can do that. But if you want every one of them present over here, you simply go to this, and all of them are placed. Okay, okay. You can see all of them are, but these all are straight lines. So what we would do, we'll simply select this and you can see a clock sign over here. So you will select it. It's like 50 is the total their duty cycle and it is 10. So I'll just give them a value of 50. Okay. So you can see over here now it's changed. Now simply I'll do this as well as 100. Okay. And last one is, so with every increase of the number input and output, I would be increasing this to 150. Okay, 150, and this is done. So now I would be running Quartes. Yes, this would be safe. So this will be running out. Now, sometimes there are many errors reduced in this Quartes circuit, but if you have done the circuit correctly, no errors would be completed. Now, most of the here I got an error, and that is permission denied and error log permission denied. So there must be some error. I'll check in running it out again. Although it was already run. Okay, so now it's run. So it might be some error that would be produced. So this is an AND gate. You can simply see it from here, the difference over here. So you can see what is the difference. The AND gate has least output. So the output result of rate of high is very less than over here that it was. So now our AND gate is proved. So we would be going to other circuits. We would be going to our OR gate. Nand Gate, OR Gate, NOR Gate, XOR Gate. So now my circuits already proved. I will simply go to them. Okay, so I'll be going to first of all OR Gate. Now, if you want to create a circuit, you have to go to a new project and visit new project visit, and it would be given. So this is now the difference between here is this only from OR gate. This is a symbol of OR gate. So as it is already run, so I'll just go to the gate node. So it is here. So it was already proved. So its waveform is also stored. So just like this, if you want to go to the process of finding and doing the procedure is the same as when done once. So you just need to just change in these expressions, just change them. The input. So NOT gate would be the most easiest the outputs. I'll be showing you the outputs after this, how they are produced and how they look like. Okay, so I'll go for here. This is an NOT gate. The NOT gate in simple, there is only one input and one output, one wire, and then you just produce y is equals to NOT of A, and that is NOT gate. So if you want to see its viewer in viewer, yes, it is proved. Now I will be going simply, I've stored the results over here. So I'll simply be going over here to my file because show you that codes and everything are here. I'll be showing you here. So after that NOT gate, we would be going to XOR gate. This is the code for XOR gate. So this is the code for XOR gate. I'll be doing XOR gate A, B, Y. AB would be my input and Y would be output, and wire could also be X or Y. So my was Y. Then assign is equal to Y is equals to A inverse XOR B. Now this is the first sign of XOR gate. This one arrowhead at the upward. So this will produce the XOR gate function. So n value and what results we are getting. This will be our waveform. This has equal distribution, the equal distribution of x, and because in this case when XOR gate we would be having that if both the inputs are the same, then it would result in a higher logic. But if both the inputs are different, then this results in the low logic. For they are two always in the forward data, there are two of them. So it is an equal circuit. One is proved, one is not. So what is the circuit implementation? And this is an XOR gate produced on Quartes. So now next we would be doing XNOR gate. So in XNOR gate, the simple difference between XOR gate from that to this is just this NOR, this not of A XOR B. So this will be produced our XNOR gate. Just by as the name identifies the X NOR X of NOR. So then we would be showing this is a circuit implement. The OR gate is already produced, and NOT gate is produced at the head. So this circuit also has equal inputs and equal output because this will have same that if both the inputs are different, then the result would be faster. So XOR gate, XNOR gate, we would be simply opening it. This is my XNOR gate produced. I'll be going and locate and viewing it RTL. So this is the RTL. The XOR is attached to a NOT gate. This is simply produced by here and its output is simple. You can also run the Okay, so this is university program. Okay, so we would be going insert node, simply doing the same functions, node, list, this, okay, okay, and then changing these, oh sorry, clock 50 plus, okay, then 100, and then 150. Okay, so now this is proved and we would be simply running it out. Yes. Okay. Um, so this is where this would be the implemented a wave that would be produced, that would be our implemented wave or of Xor Gate. This is our Xor Gate. We will recently doing it. So you can see that is the same as Xor Gate, but the difference is that where the Xor Gate would have was having the high logics, it is having low logics, and where the if the Xor Gate was having the low logics, it is having the high logics. So this is a major difference between Xor Gate and Xor Gate. So Xor Gate is when both the inputs are different, then the result of the output is positive or high logic. So, and when both the inputs are same, the implementation is low logic. So after this we have done XOR gate. Now I would be doing XOR gate is done, XOR gate is done, OR gate is done, NOT gate is done. Now it is turn of NAND and NOR gate. So NAND gate, its code is simple of NAND gate. It is the OR of AND gate. So we simply place an OR. This symbol of OR, NOT means the negative of NOT. This is the symbol of NOT gate, NOT, and we simply press present that NOT of AND gate. Okay, so the next the formula would having no change at all, just a single sign. Okay, and this is a NAND gate, and connected to a NOT its result into the NAND gate. This its output would be this, like in the AND gate we were having little outputs of high logics were very low, but in NAND gate high logics are very much. Why? Because in NAND gate it works similarly to a OR gate, mostly similar, but else than just having that if both the input are positive, the NAND gate would be 0. But in else vice versa in AND gate, if only AND gate is workable if both inputs are 1. So this is also produced over here in this circuit. Then we would be going to NOR gate, which is negative of OR gate. So I'll be simply connected over here. So this is our circuit. It is simple. We would be doing a NOT of OR gate. This is an OR gate. This is a symbol of OR, and this is a symbol of NOT. So the circuit would, the rest of the circuit is same, and this will produce this RTL, and this RTL is exactly the same that we would be producing in our Proteus as well, and this is the exact same that or NOT of OR gate. This is exactly the same. Now we will see. We will be it's in its waveform. So its waveform also explains us very efficiently what is the output. It waveform is much similar to AND gate's waveform. Now why is it? Because OR gate is only negative. Only OR gate is only negative when both of the inputs are 0. And in NOR gate, it is only positive if both of the inputs are 0. Although this if in AND gate both the inputs are 0, it will result in 0, but in NOR gate it will result in 1. So NOR is a very proficient in doing this, because in this, if we are getting an input signal of 0, it will result in a high logic. Now all of these the circuits are done, now we would be working towards these Boolean expressions, Boolean functions, and De Morgan's law. First of all, I would be saying the Boolean function that it would be an easy that we had produced in my previous video. I had already proved it using in Proteus the x and y. Its equation is a general equation over there is x plus product of y and z. So we would also be doing it the same as well. In this inputs are 3 because we are needing x, y, and z in the Proteus. So now we would be using yes a, b, and c, and d would be the output. X is my wire. You can also take d as your wire and simply write it. D is equals to a, that is over here, b, a bar, a or is the symbol over here, which means plus, b and c. You can also okay, so I've used this. You can also use that. Okay, so I'll be showing you. So there is a little problem. Okay, so I'll be going on my Boolean expression. Boolean function. Okay, Boolean function. I'll be going in Boolean function, and it is opening up. It will require some time. Okay, so here it is. I'll simply changing it because I made a mistake. So this is it. I'll simply run it up. Yes, it is modified. It would require few time, and then it will be resulted into the formation, and results would be implemented. So you need to take care of the on the symbols that are you using while using it or not finding it out. Although the function over here produced okay, the function over here is, although the function over here would be also wrong because it has an XOR gate, well my would be an OR gate and gate, so it is a mistake, but we would be correcting over here as well. So you need to learn about your things, that what you do and what you are forming. So because sometimes these simple problems create a lot of heavy problems over here in your circuit, so you need to be knowing when you change it and how you implement them. These simple circuits can the simple value, these are simple symbols, just like I have missed just one and that resulted into the whole formation as wrong. So you need to know the difference over there. So this is it. So our circuit also is proved is run over here. So it's simply going here. I'll simply go closing it, and I'll simply go over here, locate the RTL viewer, and it will take 2 minutes, few seconds. And yes, this is our circuit. Okay, so after this we would be going over here and we would be simulating its function. Let's go here, right click it, insert node and bus, node finder list, go for here, it's done. Okay, and okay over here, then we have this, we have simply go here, just oh yes, there's already 50. As you can see that I'm increasing as I'm going down, so you also have to increase it out. Like if it's 50, then its second is half 100, then third is 150, then fourth would be 200. You need to increase it simultaneously. You do not increase it in an abrupt way that one is 50, the next is 60, then for seventh is 90 or 200. So it would not be giving you an accurate and good results. You need to be changing it very proficiently. Okay. Okay. So, while talking about these waveforms, when you change their waveforms, like I've changed them, so you need to be changing them in a simultaneous way, in a simultaneous and accurate way. If you're like changing them 90, 80, 90, 80, so then that would result in a abrupt form. So now this is our Boolean function, and this is correct now. So now we were implementing Boolean first. So Boolean function that was that x not. So now we will be implementing our first Boolean expression, that would be that a naught multiplied by b naught plus c naught multiplied by d naught. That would be a naught in giving input a naught and b naught, giving the input to the AND gate, and c naught and d naught giving the input to the other AND gate, and the resultant input would be outputs would be giving the input to the OR gate, like in the function of like in the circuit produced over here, that a is not a not of a and not of b in the AND gate resulted to the e of one input, and then the c in the naught and d naught a AND gate would be presenting into the ASL. So what would be their graph? The graph is like this. So this can be produced, this equation can be produced like if both are positive, so it is a high gate, and then so like this over here, this was a simple circuit. A output, this B output, C output, D output, simple ones. Then the output is this one. So why is it this one? It is that when you implement the circuit out, if you I've already produced its graph, I'll be showing it. 1 minute. I have made it graph on made it truth table on Word document. So I'll be showing you from there. I've formatted it in the lab report, so I have already made its truth table and implemented the circuit. So I'll be using that to prove it. Okay. So the first one expression that we are using right now is this one expression, this. So if you see over here, its input says 1, 2, 3, 4 and 5 inputs, 5 ones, and then 3 zeros and then 1. So that is 1, 2, 3, 4. 5 the rest is missing, there 5, and then 3 input over here, then out 1, and then 3 and then 1. Now if you concentrate over here, this is a pattern going on, 1 0 0 3 1, then 3 zeros, then 1, then 3 zeros. This is a pattern that is the same pattern produced over here, and then this abruptly starts from this word towards the 3 as well as here. So this will also be producing like this, like the circuit is going again and again, and this will be like this is the same way. So you do not have to worry about it. This graph absolutely defines how the circuit will look like. So now this was proved. Now we would be going. Yeah, you can see that equal patterns were produced. So now I would go opening it, and then I'll be going to the next towards the next, that was second Boolean function, that is if x naught b naught, that is function having if a naught multiplied by b OR gate plus c naught multiplied by d. This is if a negative value of a that is the negative value of A is going through AND gate and B positive value of B. And then this results in the one input of OR gate, and then C negative value of C gate plus multiplied by positive direct value of D gate. So this will result in the for the next input of the OR gate, and this will result in the formation of the result. So this equation can also be proved. Now let's move on to the circuit. So it's a equation is like this. So first of all, we would be opening its Word file and looking at the circuit over here. So we would first of all checking the pattern. So first is 1 0, then 0 0, then there are three ones, four ones in multiple row. So that would be a huge input. And you can see in this is a huge input. Then this is there is a abrupt line. Then there is a three circuits. Now let's see. Then there is okay. So this one is input is starting from there here. This was one. Then there is a two scab. Then there is a three input for for ones a high logic. Then there is a four zeros like over here. Then there is a one pattern. Then there is a zero zero zero. Then 0 1 0. So this is also being proved over here. The 0 1. So if you want to check it on Quartes, we would simply be going over there. I've already implemented the circuit. Uh, Open it. Boolean expression number 2. I've already did it. So I'll be opening it out. So this Quartes is open. I'll simply go over here. So this is my circuit. Okay, I'll just going there. So everything is checked. I'll be going to university. Okay, just simply go ahead and doing the routine one. So this is a Verilog that was already proved, that was already placed with that I've already explained previously. So this was just going from 1 0 0, then the three gap, and then it is also proving the um, truth table. It starts from here, then one gap, zero gap, then there is a lead, then there's a tip of a lead, then there's a pattern going on for few seconds, then there is a dip, the greater dip, and then there is the high logic and B logic. So it would also be proved. So now we would be moving on to the De Morgan's law. That is our first one, that is mostly the implementation of the direct implementation. The Boolean functions are the implementation of the logic gates, and the Boolean then De Morgan's law is an implementation of the Boolean functions. So this is a de Mobius law first case, that is that if both if we use that the OR of A and B is inverse, or or that A um A A naught is multiplied by B naught, the result would be same. So we would just simply go to the circuit, and it proves that the circuit is the result is same. So first we will go into the circuit, then I'll be explaining you uh, the answer from the waveform. So this is the circuit. This produces that if we have simply placed an OR gate, and that is already placed over here. So we will simply take two inputs, that is one is A and one is B. Okay, then we would be placing an OR gate, and then a not of AND gate, and not of the value of A and not of the value of B, that we have already done. Like we have taken if our first expression was that if A our first input was like we have placed first expression that we have already chosen was that if A plus B is equals to not of it. So this is A OR gate plus B not of it is equals to C. This is the first question. Then the next one is then A naught over here, A naught plus B naught is equals to D, and this is our equation. Now in De Morgan's law, we have to prove that these both the equations have the same result. So we would be proving this from the our this graph over here that we have produced. So if you see both the outputs, they are same, exactly the same. This proves our De Morgan's law, and this proves that our De Morgan's law states is first for the first expression is true. Now we would be going to the second De Morgan's law expression, and we would be proving it positive. So then in the second one, instead, the first one we had taken that if if not a not of A plus B. Now in this one we would be saying not of A multiplied by B is equals to not of A plus not of B is equals to not of A not of B. So what is this equation? It is first equation that was a not of A multiplied by B. A multiplied by B not of it. The result of A multiplied by B is inverted, so it results in C. This is already in the circuit. And then that is, and the next was that A naught, then invert the input of A plus the invert input of B is equals to D. So this is also that is a circuit. Now here in this De Morgan's law graph, it absolutely explains that it is equal. From the graph over here, we can absolutely prove that this is equal. So our expression is eventually being proved that our both De Morgan expressions are proved from this Quartes graph interference. And this is the major advantage of Quartes, that you could be able to justify the waveform, you could be able to explain it. In Proteus, we had to draw multiple circuits and multiple of the inputs of Foster oscilloscope, and this interference that would be just given simply, it was not being able to produce this efficient result that is present over here in Quartes. So hope you all have got what I wanted to explain, and thank you very much for watching, and Jazakallah and Khuda Hafiz.